right. So speaking about quantum computers, so maybe I can give a short continuation of the lecture and kind of really here kind of switching gears completely and basically thinking about how to build quantum systems now from isolated neutral atoms. And against the backdrop of what I already discussed, neutral atoms have a few key advantages. First off, they have excellent coherence properties. So for example, like the world's best atomic clocks are now based on neutral atoms. So it's actually relatively easy to create system of identical neutral atoms with large numbers, and also you can couple them strongly to light. But there are also some challenges, and first off, the challenge is that atoms in general interact weakly. That's already was the problem with these atom-like defects, but the same problem occurs here. And also neutral atoms are hard to control individually in large numbers. So there are several ways to actually kind of circumvent these challenges, and but what's important is that basically like most of this atomic physics, modern atomics experiments start from this device which is called magneto-optic trap, where you basically can easily create arrays of tens of millions of atoms. So basically in terms of, and they're all identical, so in terms of like a number of just qubit, this is very, very hard to beat, and so so this source of cold identical neutral atoms are essentially unlimited, and the key challenge is really an efficient classical control. So the approach that I will now kind of introduce and we'll talk more about tomorrow involved the use of something which is called optical tweezer traps, which are basically highly focused light beams, which can basically be used to essentially trap and hold isolated atoms in a free space, in a vacuum. And the idea is essentially the following. So you can use this kind of focused beams to attract the atoms to the point of highest intensity. And the idea is that this kind of off-resonant laser beam induces a dipole, and this dipole produces a effective energy shift which actually scales like Rabi frequency divided by detuning, and as a result the atoms will be attracted to this point of the highest intensity. And kind of the overall approach here is to start with arrays of these tweezer traps and then kind of load them with single atoms. And one issue is that typically this kind of depth of this trap is actually not very large. It's maybe like in the frequency units is maybe tens or hundreds of megahertz. So what it really means is that in order for the atom to trap atom and keep it there, you need atoms to be cold, and this cooling kind of to this millikelvin kind of temperatures or sub-millikelvin temperatures is required, and this is achieved by by laser cooling techniques, which actually have been developed by our community for the last 40 or so years. So for those of you who work with solid state qubits, so these are basically kind of room temperature systems typically, but the atoms there in its vacuum tubes, and these atoms in the vacuum are moving very slowly because they are buffed in a kind of laser light, waves of laser light of certain color. So okay, so starting with this, one can think about an approach where you basically start not just with one tweezer, but with a whole array of the tweezers, and focus these tweezers very tightly, such that basically an atom is that like atoms are attracted to this highest intensity points, and actually, in fact, you can focus the tweezers so tightly that in each given trap you can have at most one atom. So if you have two atoms, they will interact and be like at least one of them will be ejected with high probability. So basically, what you will end up, if you try to just take a system of cold atoms, for example, with the mod or with optical molasses, and just load them, you will end up with the system where some traps will be full and some are empty, like is shown here. And so one way to so the system has an entropy. So one way to get rid of this entropy is to basically take a picture of this system of traps and figure out which traps are full and which are empty. And then basically what you can do once you know where atoms are located, you can either move them around, or what you can do, you can just remove some traps and kind of rearrange the rest in any desired configuration. So with that kind of approach, you basically end up with atoms sitting, a couple of micrometers from each other. So these are all kind of optically, resolvable. And as such, in these kind of systems, the atoms really don't interact. The interactions between my zero system the atoms are completely classical. To make them interact, what you do, you basically excite these atoms in the Rydberg state, and then you kind of change effectively the interaction strength between atoms, by a large number, and this, what allows you to basically, create, for example, quantum logic or do, things like this. So, okay, so here is kind of this Rydberg, kind of a short tutorial in Rydberg physics. So basically Rydberg states is something that you learn in a kind of introductory quantum mechanics classes. So these are orbits, highly excited orbits with large principal quantum number. And basically when you go to like systems with quantum number like n equals 100, your effective, kind of size of the orbit, really kind of explodes. So it can be a fraction of the micron at this point. And what, as a consequence, these atoms are highly polarizable. So the polarizability is much larger than for the ground state atoms. And in particular, then if you have two of these orbits, two of these atoms, they kind of modify each other's orbit, resulting in a huge interaction. So in fact, the van der Waal interaction scales as an 11th power of principal quantum number and can be 14 orders of magnitude larger than the van der Waal interaction between the ground state atoms. So by the way, if you want a homework problem for this afternoon, so you can try to derive, on the back of the envelope, that's 11th power. It's very instructive, Do some of you guys know? Those of you who work with Rydberg atoms. No. So where does it, how come? Where does this 11th power come? Nah? You can answer this question. So this is a radius, right? The dipole moment scales as n squared, correct? Dipole-dipole interaction would scale as n to the 4th, right? There are two dipoles. So this van der Waal interaction is like a second order dipole-dipole interaction, right? So it's basically it's 10 to the 4th to the 2nd power. It's 10 to the 8th. So where are this? The other. Where is n cube come from? Does anyone know? Huh? Yeah, exactly, because it's a second order, right? Its energy denominator is a splitting between nearby Rydberg levels, right? It basically it scales as n squared, but it's a derivative which counts as n cubed. Huh? Yeah, does it make sense? Any questions? Yeah. All right. Okay. So, you can use the strong interactions in different ways, but the way which actually is kind of really very special is the one which involves is something which is called a Rydberg blockade mechanism. And so the idea of this Rydberg blockade is the following. So suppose you have two atoms which are now sitting very far away from each other, and suppose you excite them resonantly. And if you excite them resonantly, if they are far away from each other, they will just undergo independent Rabi oscillations. However, if you start bringing them together, eventually what will happen is that this van der Waal interaction will take over. And at some point, you will not be able, with a resonant pulse, to excite both of these atoms together. You can excite one or the other, but never both. And this is because this doubly excited state is shifted away. So this distance where where you cannot energetically excite more than one atom is called Rydberg blockade. So basically simultaneous excitation is blocked at distances smaller than this RB. Actually, it turns out to be a very important, very kind of robust mechanism to entangle atoms because it's insensitive to motion and position. So in fact, this Rydberg blockade in some way makes this interaction digital. So if the atoms are far away, they're not interacting, but if they are within ring blockade, this interaction is completely suppressed. It's like infinity, to the leading order, of course. Okay, so with all of this, things, the kinds of experiments which I will be talking about tomorrow in particular, will involve essentially the following protocol. So you will start with the array of atoms unsorted, and then you sort them in desired configuration, and then basically what you do, you subject these atoms to sequences of laser pulses, and then after these laser pulses, what you will do, you will again take another image of the atoms, and in this case you will take this image in a state-dependent way, so it will be a projective readout. And so this is now, as you know, a kind of an exploding field, so there are actually over 200 experiments built around the world, and actually there are at least 8 companies who are trying to commercialize this technology. But I would actually like to point out that this is actually really an exciting frontier. So because there are now many experiments with different types of atoms. Strontium pioneered by Manuel at Caltech, and I think there are now there's probably 10 experiments in Munich, focusing on strontium. Actually, there are also, you can combine this, some of them, with optical lattices, which is also a very cool direction, which Adam Kaufman's lab. So ytterbium is another example. So people start actually building arrays from molecules. I think there will be a talk at the conference about it. And some of these things become very exotic. So this is, for example, two-species array from Hannes Bernian group in Chicago, where they're already starting to do physics. So this is actually a cesium array, which was just, so far, just atoms trapped. There is no Rydberg interactions, but the number of atoms trapped here is more than 5,000. It's actually quite impressive as in Manuel's group. So this is actually really an exciting frontier because it bridges many kind of different directions, from many-body dynamics to quantum computing to quantum metrology, and this tweezer array is actually very much complementary to optical lattice. In fact, as already mentioned, there is effort to combine both of these approaches. So there are several kind of practical considerations. So to begin with, you could say, in principle, any kind of atoms can be trapped, so long as you sort of identify right transitions. But there is always some details, so you can have a choice of atoms, either alkali atom or alkaline earth atom. And even within a given atom, you can encode qubit differently. So for example, you can either use encoding between ground and Rydberg states, or you can encode qubits in a hyperfine states, and then only if you want to enable interaction, you excite them. This atom, for example, from one hyperfine state to Rydberg. So there are also, in addition to different qubits, there are different modalities. You can either use a system as an analog system, or digital, or a combination. So this is one of the early examples, where we actually kind of studied entanglement of just atom pairs. And in this case, we use ground and Rydberg as a kind of encoding. And so in this case, you can just use Rydberg blockade to simply just entangle atoms by just exciting the atoms from the ground state to one of these entangled W states, to kind of, it's a Bell state, which is either atom in a ground state or Rydberg state, or the other way around, and you don't know which one. And so basically, by kind of, looking at this traces here. This is the probability of atoms, both atoms being in a ground state. This is the probability of one atom being excited, and this is the probability of two atoms. So you see that basically there is, due to blockade, there is no excitation at all. And so you can then, for example, by adding some phase shifts, you can actually try to kind of study fidelity of this, and this is actually an old experiment, so at this point we can reconstruct a density matrix, and fidelity was like 97%. So recent work is actually closer to 3/9, and this operation time can also be very fast. It will be kind of tens of nanoseconds. So you can also think about kind of using this system as a programmable, analog programmable simulator. And if you start, for example, with the chain of these atoms, you can think about it as a spin chain. So in the spin chain, you have basically like a transverse field. It's actually a field applied in a z direction. N is a number of Rydberg atoms in each lattice site and interaction. In fact, this gives this kind of Hamiltonian gives rise to a family of models which have actually quite elaborate phase diagram in both 1 and 2 dimensions. So in 1 dimension, basically, you can, if you don't have any interactions, basically the ground state, depending on detuning, is either all atoms in the ground state or all atoms in the excited state. But if you now add blockade, you cannot create the chain with all Rydberg atoms excited. So you basically create a chain with every other atom excited. So that's this kind of Z2 ordered state. But if you now increase blockade, you not just have a nearest neighbor, but second nearest neighbor blocked. You sort of create all of this family of states. And you can explore them experimentally with starting in a ground state and then just trying to enter all of these different phases adiabatically. This is 7-year-old result, so where you basically can create these states with basically different broken symmetry, and all of that you just basically program, in this case, the position of the atoms. You bring the atoms closer together or putting them far away so that their distance is different relative to the Rydberg blockade radius. So in a kind of modern incarnation, so many of these experiments are powered by these special light modulators, and this is basically a computer-generated hologram where basically by just programming on a computer, it's actually a device similar to what's used in this projector, which actually projects the slides. You can basically create kind of nearly arbitrary patterns of light beams in 2 dimensions. So in this case, for example, you can create an array of tweezer traps. So these special light modulators are quite amazing devices, but they have one limitation. Actually, the update rate is very slow. So if you want to move atoms, you actually want to use some other device. And actually, one device which is particularly powerful is this is a set of 2 AODs, acousto-optic deflectors, where you can actually just steer the light beams and basically move the atoms, the columns or rows. And it all can be controlled via the computer, and then basically you can start kind of creating this kind of systems. So this actually it's much slower than the experimental update rate, but you can sort of create and sort this traps, and this basically these traps you can fill with much larger than 99% probability. So you can of course create different types of arrangements, including some disordered arrangements, and this could be a starting point for some very interesting kind of experiments. So one type of experiments is an analog experiment, where you basically position the atoms in a certain way, kind of relative to the Rydberg blockade, and then basically start with negative detuning, where the array should be, the ground state should be, atoms should be in a lower state, and then you change the detuning to, for example, in this case, create this ferromagnetic state. And you can analyze the states in different ways. You can look at the 2 particle correlation functions. You can also look at distribution of microscopic states. You can also study dynamics, and in fact, from these dynamic studies, what you do, you go across the phase transition with different speed. You can, for example, extract things like critical exponents, and these are the tools which actually are used now, across the community in many different experiments. So the kind of stuff which I will talk tomorrow about will utilize the third generation of the experiments in our lab. And so in this third generation, so we utilize these techniques, SLMs plus these cross TODs, to have larger systems, high fidelity, and actually much more advanced control. And so by now we can actually form arrays with actually now more than 500 atoms, but in particular we have all sorts of tools to, for example, address atoms individually, move atoms around, do single qubit rotations and things like this. I will talk about this tomorrow. So this is actually some examples of the recent progress. So all of these things are kind of analog systems, and actually the Quera machine is also an analog system, but actually the stuff which I will focus on tomorrow will involve mostly digital processing. So just, I will maybe have 2 more slides, and then maybe we can have stop for discussion. So basically, like the difference between this analog and digital, as I say, is not very sharp, but so like for analog systems, mostly we and ours are using this ground Rydberg basis. And, it actually has some positive features, but also limitations, because Rydberg state, for example, does not live forever. And also Rydberg atoms cannot be trapped, which actually would sort of limit how long the evolution is. But kind of to really do quantum computing, what you want to do, you want to store qubits in long-lived states, for example, in these hyperfine states where the memory can be kind of easily seconds, and then only when you need to is to excite atoms from the ground state to the Rydberg state with a short laser pulse. And in fact, this is like something which we originally thought about as going, as long back as 2000, kind of the approach. But actually, it kind of took quite a number of years to really bring this approach to the point where it's like really competitive, and in fact, in the meantime, probably is a leading approach to the quantum computing. And there are a few things which actually resulted in this. One of them is this idea of creating the arrays. Another one is actually a new ways to do quantum gates. And in fact, this this development started from 2019 with this kind of idea of Levin-Pichler, what we call Levin-Pichler quantum gate. So in this quantum gate, what you do, you basically use this blockade and you eliminate both atoms with the Rydberg state simultaneously to create this kind of conditional phase shift. And so basically the idea here is that you kind of engineer your pulse sequences such that your states, with either one atom in this state 1 or 2 atoms undergo exactly the right kind of dynamics such that they are brought back to this state 1, but they are brought back with different phase, depending on whether you had one atom initially in a state 1 or both. And kind of understanding that is actually a very good exercise. It tests your knowledge of the Bloch sphere. Bloch sphere is one of the most useful concepts which you have to learn. By the way, for this summer school, so there are 5 things which you have to know about quantum optics. And you have to remember them very deeply, remember them in your sleep. And if you know them well, you can do amazing things. So Bloch sphere is one of them. Do you know what are the 4 others? You don't know? Wow. Huh? Well, once you understand Bloch sphere, radio oscillation is kind of trivial, Huh? It's really quantum optics. There are 5 things you have to know. That sounds good. So the limitation of Bloch sphere is that only is effective for qubits. If you go to larger systems, it's very hard to basically like use the block sphere. So in fact, the concept of the rest atom provides the ways to understand complex interactions in kind of multi-state system. Multi-state system. Okay, that's 2. What are the other 3? It's kind of interesting. So yes, indeed. So indeed, for at least quantized atom field interaction, the concept of correlation function is very important. So I would say actually the underlying concept is a coherent state, right? But sort of from the coherent state you can build correlation functions. Okay, 3. Yeah, I'm very generous with grading. So, but you have 2 more. So one is semi-classical and one is quantum. So there is a semi-classical concept which is super important, and the reason is this block sphere and the rest state involves only coherent atom-photon interaction. But if we only had coherent atom-photon interaction, most of you guys would be doing something else. You would be doing, superconducting qubits, Huh?
The blockade model for the
Nah, it's not as no, but it's involves something which is not coherent. I mean, yeah, a little bit, yeah, exactly. So it's kind of, it's more, okay, the real concept is a golden rule, but golden rule, what? Well, okay, I have an emotional attachment to electromagnetic, but it's not a part. I mean, if you use these 5 rules, you can understand electromagnetic, but no, but it's really like golden rule and optical pumping, actually. Optical, it involves a combination of spontaneous emission and excitation, but because, this is what optical pumping is used to prepare pure states, it's used to cool atoms, and it's it's a physics of golden rule, basically. It's a coherent excitation and the perturbation. Okay, it's 4. Then there is a 5th one, and the 5th one I even kind of talked about today, nearly talked. It's connected to cavity QED. The model is not a concept, but there is something in James Cummings model which is super important, which is central, which goes to exponent of graduate student happiness, quality of life. So it's this 5 concept goes to the exponent of graduate student quality of life. Especially if you do cavity QED or something like this. Huh? Nah, synchronization does not go to your quality of life. But there is one thing which makes us cavity QED, either super hard, or, very pleasant, Nah, this is not really true. It's a quantized, it's a property of quantized. It's actually single photon Rabi frequency. The Rabi frequency associated with single photon. Remember when we talked about squeezing, the photons, into small cavity. The reason why you do it is because you want your G to become as large as possible. And it results in this single photon Rabi frequency and this kappa, the cooperativity, are the 2 things, Yeah, these are 5 things. If you know these 5 things, you can really rule the world, if you know them well, So an example. Okay, so I can tell you, going back, 2000 and 2001, I myself, together with, by then already famous, I was a postdoc, with famous researchers like Ignacio, Peter, Dieter Jaksch was also a co-author, Luming Duang, so we spent a lot of time trying to figure out how we can actually do the kind of gate, Rydberg gate, efficiently, without addressing atoms individually, in a way which is fast and robust. So we could not figure it out. I personally spent several months. So this guy, and actually it's Hannes and Harry. So Hannes kind of had an initial idea. That same afternoon, Harry implemented it experimentally, and the fidelity up to that point, the highest fidelity was 80%. And I think that really started this new kind of development. So there is another one, which actually is also, I will talk about it tomorrow, which actually I think was also very important, is this idea of reconfigurable architecture. And the idea here is the following. So, you can store this qubit here for a long time. in a tweezer, but actually it turns out not only you can store it in a stationary tweezer, you can move the tweezer around without destroying coherence. So, and you can, for example, in this first experiment, you move it across the field of view of the objective, and in this case, you prepare the entangled state, you test the entanglement, in situ, and you test by spreading, and it's basically, you see that it's completely preserved. So, okay, so these two kind of ideas, resulted in what I believe is actually by now a leading platform for quantum computing. And that's kind of this reconfigurable architecture. And that will be a subject of tomorrow's talk. Maybe even that slide is a nice kind of culmination of that. So there are many interesting opportunities.
Right. Thanks a lot for this very nice introduction to neutral atoms and quantum computing. Do you have any questions?
I hope the question's not too political or so, but you mentioned there's different labs using different elements. Mm-hmm. Do you have a perspective on why you're using rubidium while others are now testing others, or
So it's kind of, to begin with, you could say they are all similar approaches, but at the end, the one which is like best might depend on what the purpose. For example, if you want to use, if you want to build clocks, you certainly should use strontium, not rubidium. But basically depending on kind of application, depending on what you want to do, basically there is maybe a better atom. But the jury is still not out, on that. And I can tell you that rubidium has actually a very favorable combination in terms of Rydberg interaction of these quantum defects, kind of, NC6 coefficient. So basically this Rydberg, and this physics error is that Rydberg blockade is only an approximation to the full story. In particular, when the atoms come very close to each other, there are like a lot of, there is something which is called spaghetti, there's a lot of levels. So you would like to basically have a nice clean range of blockade, where, the shifts are already larger than like Rabi frequency, for example, and you're not limited by this spaghetti. For that reason, rubidium is kind of special, but there are also other, for example, storing a lot of atoms is a little bit easier for some wavelengths. So basically, in my opinion, I think it's great that many of them are being explored, and I think, I could maybe my complaint about some of the other platforms. Is that people kind of settle too early on one kind of design, and then somehow 10 years later they realize that you cannot go on with that. So for that reason, actually, I think it's very good, And in fact, maybe even one would start using a combination of, like you would use strontium and rubidium. Strontium you use for clocks, and rubidium maybe you use for kind of large scale, operation or something like that. So,
Thank you for the very nice talk. Do you have a universal set of quantum gates that you can apply in this platform?
Yes, actually, since about a year, actually. So we can apply universal set, and basically, and I think I'll talk about. So basically, the way how you do it is you can apply single qubit rotations by using basically these two crossed AODs. You can eliminate patterns of atoms, individual or in parallel of selected atoms. Then you can use Raman transitions to basically rotate them, right? And then in combination with the CZ gate as a universal, actually what is most important here is that you can do these universal operations in a highly parallel manner. And this parallelism is something I will talk about tomorrow, is very special to this platform. This is something that, for example, superconducting qubits just, really, have a hard time to achieve, But there is a lot of work on this, but yeah.
Thanks.
Yeah.
Do you sometimes in your laboratories or in your experiments end up in the situation where any of your experiments is limited by the frequency stability of the lasers you use?
Yes, so yes, and in particular this Rydberg excitation transition. So you like, I mean, in our case we use 2-photon excitation, and there the absolute frequency, like drifts and so on, is important. And we are worrying about all of these things like phase noise and so on. In fact, we use some techniques that our colleagues have developed, including, for example, cavity filtering. And these actually have been quite instrumental in terms of getting to, so right now the state of the art is, we can have, highly parallel gates on over 100 of atoms in parallel, with fidelity over 99.5%. And some of these imperfections are due to this, phase noise of our lasers. And we, of course, we are constantly trying to improve them, right? So, yeah.
Thanks.
I mean, for Rydberg, for the lower, for this kind of, for the single qubit operation, we use Raman transitions. They are not absolute frequency, absolute drifts are not important. Yeah.
More questions? Otherwise, while people think, maybe I can ask a question. So especially for these larger arrays, how do you, or what do you think is the best approach for local addressing it? Is it like having the interaction zones more or less, or are you actually trying to have like with an AUD, for example, or SLM, DMD local addressing in your system?
Yeah, the answer is both. I think you need both. So, so it's maybe some one of the slides from. Let's see if I can find. So basically, yeah. So like these are like some of the more recent, work that we have basically from last year. So this is, as I already mentioned. So we can now have 2 qubit operations with fidelities more than 99.5%, and it has been like basically the progress has been quite rapid here. But in addition, so we also implemented this kind of this individual addressing, and this was done by these 2-crossed acousto-optic deflectors. So we actually love these acousto-optic deflectors. So we have 3 sets of them already for different purposes. So this individual addressing fidelity is a little bit worse than the global single qubit addressing fidelity, but there is no fundamental reason. I'm confident that 4 nines, but will be there, and probably 6 nines if one works hard. And finally, this zoned architecture, I think, is also very, very important. In fact, so we now work with these systems where we have like an entangling zone, we have a storage zone, and we have now readout zone for mid-circuit readout. So I think combining these two, and these zones can be actually, in principle, reconfigured dynamically. I think all of that will be super important, And these are these ingredients which I will kind of talk about tomorrow about this, for example, like which go into this logical processor. I mean, so you really need these zones, and this actually makes efficient control over these qubits stored over these zones is what makes this approach very, very special. In fact, it starts now looking like a real, computer. So, yeah.
Thanks a lot. Do we have another question out of the audience? We still have more than 6 minutes left.
So thank you. On your last slide, I think the title was Analog Digital Quantum Simulation, and I know that people are trying to do this with fermions, so where you say, okay, you encode the fermionic statistics by braiding literally the atoms. And in your platform, what are the ideas to do analog digital hybrid simulation?
Yes. So actually this fermionic, I ran out of space on this slide. It actually was here, but for some reason, like for the last talk I gave, it was this ADS-CFT was more, but so this indeed you can in principle utilized by combining optical lattices with these tweezer arrays, you can actually utilize natural encoding into fermionic degrees of freedom, which can be kind of quite powerful, quite efficient. Unfortunately, the conditions for this kind of to utilize these fermions and combine it with the kind of techniques that I am describing here are actually quite stiff, because basically this fermionic degrees of freedom will be, for example, sensitive to like essentially like light shifts at a very small scale, at the phases produced by these light shifts. So I think this is doesn't seem to be completely trivial, but I think it's an exciting next 5 years. I wouldn't be surprised, you know. So fermionic degrees of freedom are also quite hard to manipulate in the sense that, for example, something like spin echo, which we take for granted here. So we do like thousands of spin echoes in each experiments, you know, for fermionic degrees of freedom is highly non-trivial, you know. So I think, and moreover, it is not obvious how to do error correction for fermions. So I think simulating fermions is an exciting frontier. And I would say that there are ways to do it using spin encodings. There are maybe ways to do it using this kind of hybrid, you know. We have to see how it's going. So for example, if you start working with logical qubits, sometimes these fermionic degrees of freedom appear very naturally there. So it's kind of, you know, but I mean, this is a kind of stuff which I think next, you know, 2 to 3 years absolutely will be explored experimentally. Mm-hmm. So, and it's also related a little bit to this lattice gauge theory, simulation, and so on. Yeah. Yeah.
Thanks.
All right. Last chance for another question. I'm going to wait the obligatory 10 seconds. Dead silence.
Good.
Amazing.
Right.
Then let's thank Misha again for this very nice introduction. And of course, we have a small gift from the MCQST community for you, for your beverage of choice for tonight.
Okay, thank you so much.
And I'm sure if anyone else has any further questions until tomorrow, you're very happy still to talk to us and answer them.
Yeah.
So
thank you,
thanks a
guys.
lot.
Thank you so much. Yeah.